because we do polarization, right? The polarization homework is very trivial. Plot 3 or 4 points, see the way the tip rotates, and you can identify. If it's linear, if it's right hand, left hand, circularized, or circularly polarized, or elliptical. That's the easy way to do it. Remember that. Don't ever worry about tricks with those equations. They're not much book. Next, so we're all good. So this is a rare thing. Okay. So now we're going to be talking about the last topic, which is reflections from surface. There are only going to be waves that are normally incident. So let me explain this. Remember how I was talking about how with radar, if you sent out a right-hand circular polarized wave, it would come back left if it was a conductor, so you would know it's the reflected signal from your radar and not a jam. Do you all follow me on that? All right. Now we're going to talk about the mechanism of reflection. And what we do is we assume a plane wave. This is reflection. By the way, these are brand new markers from, well, I should say, markers that are just fresh in from the box in there, but I don't know how long they've been there, because these things basically seem dry to me. This is irritating. Oh, this one's better. All right, so it's reflection, but it's going to be for normal incidents only. So it's normal incidents. All right, what do I mean by normal incidents? Let's do this. Here's going to be a demarcation between two regions. We're going to call this region 1 and region 2. And I'm going to try to be as consistent as I can with Wentworth's book. In region 1, it's going to have some characteristic impedance, some eta 1. It's going to have some beta, well, I'll call it beta 1 here. In region 2, you have some eta 2, some beta 2, and it can be, you can divide this differently. It could be just intrinsic properties. I could give you the frequency, the value of U, and epsilon, the sigma in each region. So either way, we'll do it. And I'm going to assume that this is the z-axis here. And I'm going to have an electromagnetic wave coming in this direction. It'll be polarized in the x direction, so call this the x direction. And this will be some incident E field. Now I'm just trying to give you sort of an idea of what's going on. When this thing hits this region, some of it is going to go through. We call that transmitted electric field. And some of it is going to be reflected. Now that's the basic concept, and this should make sense. A wave comes in, it hits, some goes through, some is reflected back on, right? We're going to do this for lossless media for right now, but it doesn't really matter. So your equation, a standard equation, the phase domain for the incident field, that would be a wave propagating to the right, would be some E naught incident, then e to the minus j beta in region 1 z ax. Does everybody recognize that as a wave moving in the positive z direction, ax polarized? Y'all follow me? That's the incident wave. There's also going to be a reflected wave. The reflected wave is going to have some E naught reflected. That's just a magnitude of it. It's still in region 1, but it's going to be e to the plus j beta 1z, and it would be in the ax direction. Y'all follow me on that? The only thing that's changed now is the magnitude's going to have a change, and the direction is now opposite. Follow me? Y'all see it's positive j beta. Can y'all see it from back there? And finally, you're going to have a transmitted field. You're going to have some E transmitted. And that's going to be some E naught transmitted. I'll just put T here. E to the minus J. Here it's going to be beta 2, and it's going to be times, call it beta 2 in the Z times Z, in the AX direction also. Those are the three components of the electric fields. And these are just, these are by definition, because we're going to be in a phasor domain. Now, they give rise to magnetic fields. The incident field here will give rise to an H incident that's going to be 1 over 8 in region 1, right? Direction of propagation crossed into the E field. Incident times E to the minus J beta 1 Z AX. Y'all follow me on that? I'm just using the definition that I showed you when you have propagating plane waves, and if you have either one, you can get the other using this definition. Do y'all remember this? This is the first definition. So what is the direction of propagation for the incident wave? What, in other words, what is AP? Positive AZ. Do you all see that, class? Can you all see it back there too? All right. Positive AZ. I'm just going to replace it. Now, one look at that, and you can see I've got AZ crossed and AX is AY. Do y'all follow me? So this is better, can be rendered as this. It's going to be some E naught incident, then it's divided by eta 1, and then it's going to be times E to the minus J beta 1 times Z, and it's going to be in the AY direction. So that's going to be the actual magnetic field that's coupled or associated with the incident field. Next, after that, I'm going to get the magnetic field for the reflected wave. So it'd be H reflected. That's still 1 over eta 1, right? We're still in region 1, right? Now what's the direction of propagation? Because we're using, remember I had 1 over eta AP crossed into the E field. So what's the direction of propagation for the reflected wave? Minus AZ. Right? Crossed into E naught reflected E to the plus J beta 1 Z AX. And if you look here, everything's the same except for that negative sign in terms of the crossings. Do you all see it? So here we're going to have a minus E naught reflected over eta 1 E to the plus J beta 1 Z AY. It's important to realize that this now has a negative sense to it. And here's one thing I'm going to say right here to make sure you get this, because this is simple, but it's important. Anytime you're wondering if you got the sign right in this stuff, always remember, if you use the right hand rule and take your index finger, put it in the direction of E, and cross it into the direction of H, your thumb points in the direction of propagation. Y'all follow me? So if you work this, for the incident field here, that's X, so Y would be coming out of the board here, and if you look at this, you got E crossed H, which is positive there, right? Direction of propagation, easy, you're right. Here, for the reflected wave, I've got E crossed into H, H is minus, right? Is going to be in the minus direction, it works. Finally, for this one, for the transmitted H field, I get 1 over eta 2, now I'm in region 2. What's the direction of this one? Just to be consistent. Come on, it's not a trick question. It's positive AZ, isn't it, class? Direction, right? It's propagating. So it's going to be positive AZ crossed into the E field here, which is going to be E transmitted 0 times E to the minus J beta 2Z in the AX direction. And you'll notice for this one, it's going to have the same exact form as the incident wave because they're both propagating in the same direction. It's going to have a positive sense to it. I get AZ crossed AX is AY. I get E naught transmitted divided by eta 2. Then I have E to the minus J beta 2Z, and it's going to be AZ crossed AX is AY. So now I have the field components. I have all the incident, reflected, and transmitted E field components and all the associated incident, reflected, and transmitted H field components. Y'all follow me? Now, the way we go about figuring out the relationships between transmitted and reflected I'm going to erase this, is very simple, because at the boundary, right here, at that boundary, the tangent electric field, E tan 1 is E tan 2. Do y'all remember that? And H tan 1 is H tan 2. There are no surface currents. Y'all hear me? So now we just equate these. And I made sure that the boundary was at z equals 0, or it gets a lot more complicated. And you'll see why in a second. So now, when I come here, these are the boundary conditions. Right here. We have E tan in region 1 equals E tan in region 2. Tangent E field. Well, here are the E fields, right? The E field in region 1 would be the incident and reflected field. It is at z equals 0, but it's just on the negative side of it, if you think about it. So what I can do is say that, and if you look at this, when I take the incident field plus the reflected field, that's the tangent field in region 1, is equal to the tangent field in region 2. It's just this. Now notice z is 0, so what happens to all these exponentials right here? They become 1, right? E to the 0 is 1. Y'all follow me on that? So here I have E naught incident plus E naught reflected is equal to E naught transmitted. I'll just put a T there for transmitted, okay? The way the book does it is different. It's easier to see it this way. Now for the H field, H tan 1 is H tan 2. Well, yeah, bless you. What's the H field in region 1? It's the incident and reflected, right? It's just on the negative side of z, you might say. So it's going to be these two, where it's equals 0, so the exponential doesn't matter. And here I have what? E naught incident over eta 1, but minus E naught reflected over eta 1 is equal to E naught transmitted over eta 2. Do y'all follow me on this? No? How many do? All right. The only thing I've done there is equate them at the boundary. That's z equals 0. So the fields on one side equal to the fields on the other. Y'all follow me? That's it. Now the rest is sort of self-evident, except we now define a couple of coefficients. We define the reflection coefficient, all right? And this is, I'll call it R, doesn't matter, but this is the symbol gamma is the reflection coefficient, will be equal to E naught reflected over E naught incident. Do y'all follow me? Yep. Okay. So now, here's what we do. I'm going to take this equation and I'm going to replace E naught transmitted by these two. Y'all follow me on this? I'm just taking this equation right here and I'm going to stick it in there. So now I can say that E naught incident over eta 1 minus E naught reflected over eta 1 is equal to E naught incident plus E naught reflected, both over eta 2. Y'all follow me? Take a good look. I'm not trying to confuse you, I'm just trying to make it as simple as I can. And now, we're going to divide everything by E naught incident. Y'all hear me on this? So, doing so, what do I get? I get 1 here, don't I? I'm going to do it right here. Then, when I get E naught reflected over E naught incident, I get the reflection coefficient. Over here, I'm dividing by E naught incident, I get 1. And then I get the reflection coefficient. Y'all see where I'm going with this, huh? Y'all agree with that? Now, eta 1 and eta 2 are known. Y'all follow me? Now I rearrange this so I can get the reflection coefficient. It really doesn't matter how you do this. If you want to, you can multiply by eta 2, right? And then you would take eta 2 over eta 1 term on this side and rearrange it, right? No matter how you do it, we can do it several ways. It ends up with the reflection coefficient being equal to eta 2 minus eta 1 over eta 2 plus eta 1. And that is E naught reflected magnitude-wise over E naught incident. And this is called the reflection coefficient. Right there. It's the voltage reflection coefficient. What does that remind you of? Think of transmission lines. What was the reflection coefficient for transmission lines at an interface? Always the impedance you're going into minus the impedance you came from, characteristic impedance over the sum of the two, right? You see how it's the same here? It's the impedance you're going into, A to 2, that's the second region, minus the impedance you came from over the sum of the two. They're always the same forms, which is nice. You see these patterns, engineering, this stuff becomes very clear after a while. All right, now when we do that, did you have a question?
I'm not sure. I was trying to understand why it was like that exactly.
You mean the proof?
Yeah, pretty much.
You see what I did here?
Yeah.
Just watch me for 1 second, all right? All right, what I'm going to do is this. I'm going to go ahead and multiply everything by A to 2 first, all right? With me?
Yeah.
Now I'm going to go ahead and multiply everything by A to 1. So that goes away, right? And then I get A to 1, right?
Yeah.
All right, now I'm going to take this term to that side and this term to this side. Y'all follow?
Yeah.
So what's going to happen then is this. I have A to 2 alone, right? Now I'm going to take A to 1 on this side, right? That's going to be equal to, I already have A to 1 here, and it's going to be times reflection coefficient. That's minus, so it becomes plus A to 2 times gamma. Or I factor out gamma, and I get A to 1 plus A to 2. You see it?
Yeah, I think so.
And then divide everything by A to 1 and A to 2, and you get
Okay.
and lo and behold, that's gamma. That's it.
Okay, thank you.
Anyway, that's just standard manipulation, trying to solve for one variable. Now that we have that, we're going to go over here and we're going to do a few things. The first is, I can say now, well, let me be clear about this. I'll do it over here first. Now I can say, if this is region 1, and this is region 2, A to 1, beta 1, beta 2, beta 2. Now I can say, since this is going to be the z-axis, and this is the x-axis, that when I take a look at the total field in region 1, I'll call it E1. Actually, this is the total field. It's the incident field. And here I can just put E naught incident outside. And it's going to be times E to the minus J beta 1, right? Just follow me on this. Plus the reflected field. Well, the reflected field is just going to be the reflection coefficient, right? Times the incident field, right? Follow me on this? And it's going to be that times E to the plus J beta 1. It's in the AX direction. Now that's the total electric field in region 1. Y'all follow me? Here's the incident part, right? And if you think about it, this is what? E reflected over E incident. So when it's multiplied by E incident, it's just E reflected there. Y'all see this? It's a shorthand way of writing. That's the total electric field in region 1. The total magnetic field in region 1 will be what? Well, it's going to be this and this, right? And if you look at this, it's going to be E naught incident over A to 1, and then it's going to be times E to the minus J beta 1 Z, but then it's minus the reflection coefficient, right? Because remember, there's a minus sign over there. Take a look. Y'all see it? it's gonna be that times e to the plus j beta 1z, and it would be in the AY direction. Now that's the total magnetic and electric field in region 1, written using a shorthand notation, the reflection coefficient. Okay. Yeah.
For the H field, is that e to the negative j beta c minus the reflection coefficient, e to the j
Yeah.
beta? Okay.
It's positive. The only thing you do, reflection coefficient is E what? Reflected over E incident? Well, when I take that and multiply it by E naught incident, I get E reflected. And that's what I want. So, and I'll put AY here, make it a little clearer.
They're negative.
Okay. Now, that is the, do you have a question?
I think get rid of the z and the like e to the j beta z in the total electric field. We're missing z's in the exponentials.
Oh, thank you so much. You are right. You are right. Thank you. All right. But that's the electric field, magnetic field in region 1, the total. And in region 2, you really don't need it. But I'm going to show you something. Actually, let me show you. Now, remember, a to 2 minus a to 1 over a to 2 plus a to 1 is the reflection coefficient, and that is a relationship to E naught reflected over E naught incident, right? This is the reflection coefficient. The transmission coefficient is E naught transmitted over E naught incident, and that's actually equal to 2 a to 2 over a to 1 plus a to 2. We can prove that too if you want, but I can get that pretty straightforward. When you take a look at the incident plus the reflected field here and use use the equation for it, set it equal to the transmitted field, we do the same thing. We just don't now then divide everything by the incident, or everything by the incident field, and we set it up at the transmitted field, not the reflected field, and you'll get this. Now, how many remember when we had transmission lines, the 2 times the impedance you're going into over the sum of the 2 was the transmission coefficient? Do you remember that at all? All right. It's true. Always. Okay, so you've got transmission and reflection coefficients. So over here, I can say the transmitted electric field in this region would just be the transmission coefficient times the incident electric field times e to the minus j beta 2z ax, and the transmitted magnetic field in region 2, well, it's the only transmitted field, it's transmission coefficient times really E naught incident, but this is over a to 2, and it's going to be times e to the minus j beta 2z ay. And that's it in a nutshell for transmission and reflection coefficients for normally incident waves on a medium. So in Dr. Wentworth's book, he has, this is the equation. That's how it was gotten, it's developed. And now, what I've just done is on page 353 through 350, really 356. And Whitworth gives you some examples of this, but here's the other thing I didn't cover yet. All right, these are the electric and magnetic fields, right? So far, we're assuming a lossless region. Now, it doesn't have to be lossless, but can we get the power in each one of those regions? Y'all follow me? Power density, I should say. Power density, first of all, if it's lossless, it's simple to get. For this waveform, I'll go over here to power. So if you take a look at this, that's the incident electric field. Well, what's the power in this? The power density, I should say. The average power incident, right? We could get it by taking 1/2, right, times the magnitude of b squared over the magnitude of eta times the cosine of the angle associated with the impedance, and then put it e to the minus gamma, see if it was lossy, but this is lossless so far. So the average power is just going to be what? 1/2 magnitude of the incident field strength squared over magnitude of eta 1, right? And it would be going in the AZ direction. Y'all follow me on that? That's for lossless region, that's it, correct class? Now for the, can you see it back there? I'm making sure. Whenever I see somebody struggling or squinting, I'm worried. Okay, everybody with me? What about the reflected power? This is going to be the average power reflected. Well, that would still have the form of 1/2, right? Magnitude of the reflected field. Notice the reflected field you can get by doing what? Reflection coefficient times incident field, and squaring it, still divided by eta 1. But what direction is it going in? Everybody see it's minus AZ, correct? It's going in the minus AZ direction. And finally, for the transmitted power density, that will be 1/2. Here, instead of the reflection coefficient, you put the transmission coefficient times E naught incident squared over, now this is eta 2, and it would be in the AZ direction. It would be watts per meter squared. Y'all follow me? Now here's the one thing that should make perfect sense. The power density of the incident wave will be exactly equal to the power density in the reflected wave plus the power density in the transmitted wave. That should make perfect sense to you. Y'all follow me on that? Let me go a step further too. The actual transmission coefficient is 1 plus the reflection coefficient. So if you have the reflection coefficient, you have the transmission coefficient. As a matter of fact, we can play all sorts of games on this, but now, if I have an incident wave and I know the material parameters across the boundary, I can get both the transmitted and reflected electric fields and magnetic fields and power densities. So it's more or less, I've characterized the region any way I want to. In Whitmer's book, Stu has, let's see, he gives problems that just make you aware of how to determine values of omega and beta in different regions and the power densities. So, if you look at all these are fairly straightforward. All right. So if you look at problem 6.38, I want to do this right here. Is it warm in here? Is it not that warm? Okay. Seems warm. this problem says you got region 1, region 2. This is z equals 0 as the dividing line. Let's see. He's got epsilon relative over here of 16. This is air. And he gives you this. He gives you the transmitted H field is equal to 12 cosine of omega t minus beta z, beta 2z, pardon me, in the AY direction, and it's milliamps per meter squared. And he wants the incident electric field, and he wants, what else? Find the reflected power density time at, so he wants P average reflect. That's what he wants. All right. Let's talk about this and see what we can get. First, looking at this, you'll notice he doesn't give us a frequency. The only thing he doesn't even give us the value of beta 2. He just says we'll call it beta 2. Now, y'all realize there's nothing to indicate loss. It's lossless, right? If that's the case, if I talk about eta 1 here, eta in region 1, that's just eta naught, or that's 120 pi, isn't it? Because that's free space, that's air. Y'all agree with that, class? Everybody? Remember the general formula for eta, square root of j omega mu over sigma plus j omega epsilon. On this side, it's air. There is no sigma. It's 0. Epsilon relative is 1, mu relative is 1. It reduces to 120 pi ohms. Y'all with me? Okay? Now, second, when we do beta, right? If it's lossless, we know gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. We know that. It's equal to alpha plus j beta. But because it's lossless, sigma is 0, and that means beta is just equal to omega times square root of mu epsilon, right? Follow me on this? And you also know that because this is free space, this is just omega over c would be beta in region 1. I'm just going to cap that. We don't know what omega is yet. Y'all follow me? I'm just showing you this. Now, go over here. This is also lossless. So in region 2, by the same logic, beta 2 would be omega times square root of mu in region 2, epsilon in region 2. Well, that's going to be omega times square root of mu naught, epsilon naught, times the square root of mu relative, which is 1 epsilon relative, which is 16. Y'all follow me? I'm putting it down so you can see the logic here. What might I do next, anyone? Take a guess. Why do you think I broke that out? Let me ask you this. Yeah, I'm going to divide by 1 over speed of light. So now I can say that beta 2 is equal to omega, right, divided by the speed of light, and the square root of 16 is 4, right? Agree with me? And that means if I think about it, I look over here, and I have beta in region 1 is omega over c, right? Well, omega over c is really beta 2 by 4, isn't it? Right? So I come over here, and what I can say is, in this region, beta 1 is omega over c is beta 2 over 4. So if you give me beta 2, I'll give you beta 1. That's it, right? Also, what do I know about the intrinsic impedance of region 2? Well, in region 1, it's 125, say it not, right? Over here, we have, it's lossless, so it's going to be square root of mu over epsilon. Sigma plays no role, the j and omega is canceled, right? Keep going on this one. I get the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative, since it's lossless. I did this for a reason. I'm going slow here. I want you to see it. Why do you think I did that?
Mu naught over epsilon naught was 125.
Right, exactly. So now I can say that this is really eta naught, or 120 pi, right? Times the square root of mu relative over epsilon relative, which is, well, mu relative is 1, epsilon relative is 16, right? That's 1 over 4, isn't it? So this is eta naught over 4. Okay? Y'all follow what I'm doing here? I'm just trying to make sure you see the logic to everything. Now, I've got the transmitted magnetic field in terms of a time domain form. What I'm going to do, just to try to show you the completeness of this problem, do everything at once. Get rid of this. Okay. So now for the transmitted side, I really have H transmitted in a phasor as some 12, right? Milliamps, I'll put times 10 minus 3rd second times e to the minus j beta 2 z ay milliamps per meter squared. I know that my eta 2 is going to be equal to eta naught over 4, right? Y'all with me on this? We find that. So if I wanted my E transmitted here, the transmitted field, if you look at this, how would I get the transmitted E field? It would be what? Minus eta in region 2 times unit vector in the direction of propagation crossed into the H field in region 2, right? Which would be the transmitted H field. Do y'all follow me on what I'm doing here? Okay? That means the transmitted field would be equal to minus eta naught over 4. Direction of propagation is what, class?
C.
Pardon, say again? AZ, exactly right. Right? And then it's going to be crossed into the H field, which is there, 12. I'm going to put times 10 to the minus 3 here. Times e to the minus j beta 2 z a y. That means the transmitted E field is going to be, well, I'm going to have 12. I'm going to have minus, well, actually, what do I have? AZ crossed AY is minus AX, where the minus is plus AX. So it's going to be plus AX, and it's going to be eta naught times 12 times 10 to the minus 3 over 4 e to the minus j beta 2z ax, and that would be volts per meter. Y'all agree with that? We'll get rid of that. Can somebody just do this for me? Take eta naught and multiply it by 3 times 10 to the minus 3rd. It's 12 over 4 is 53. Just take. Pardon?
1.13.
Is that right?
Yeah, that's right.
1.13 e to the minus j beta 2 z, the AX direction, volts per meter. All right, we've got the transmitted electric field. Next thing we need is gonna be the reflection coefficient, right? That's eta 2 minus eta 1 over eta 2 plus eta 1, correct? Or actually, transmission coefficients, even easier. 2 times eta 2 over eta 1 plus eta 2, right? Y'all follow me? I'm gonna do transmission instead of reflection, because we've got the transmitted field, that's the reason. When I take a look at this, what do you see you get? I got 2 times eta 2, right, which is eta naught over 4, over eta 1, which is eta naught, plus eta 2, which is eta naught over 4, correct, class? Now, the first thing you realize is eta naughts go. They're on top and the bottom, they go away. So now, with the transmission coefficient, what do I get? Well, I have, I'll put it this way, 2/4 over really 5/4, right? Or I have 2/5, don't I? Class?
Yes.
So that's 0.4. And that transmission coefficient, yeah, bless you, is going to be the transmitted field over the incident field. I did this for a reason. We have the transmitted field's magnitude, electric field. That's right here. And now, we want the incident electric field. I'm just being clear on this. Everyone following on this? So if I take a look at this, the incident electric field itself is going to be what? That's going to be equal to the transmitted field's value divided by 0.4 or multiply by 5/2. And what does that come out to be?
2.825.
2 point what?
825.
Volts per meter. I got the incident field strength. You wanted the reflected power density, right? We could get now the power density of the incoming wave, right? If we wanted the well, might as well get the reflection coefficient. What's the reflection coefficient going to be? Eta 2, right, minus eta 1, I'll put it down, eta 2 minus eta 1 over eta 2 plus eta 1. So that's eta naught over 4 minus eta naught over eta naught over 4 plus eta naught. So that's 1/4 minus 4/4 over 5/4. So that's minus 3/5, right? 3/5 or minus 0.6. Correct, everyone? So we can get the electric field, the reflected electric field, which is going to be, that's minus 0.6, which is it's going to be equal to E naught reflected over E naught incident. And if you want to give it to me, you can. That means the reflected field strength is what? Minus 0.6 times the incident field strength. Anybody want to tell me what that is? 2.825 times 0.6. Say again?
1.70.
Minus 1.70 volts per meter. Second on that one? Anybody? Yeah? All right, we've got the electric field strengths, incident, transmitted, and reflected. If I want the power density of any of the waves, transmitted, reflected, or incident, the only thing I have to be careful of is making sure I use the right eta. Y'all hear me? Because it's losses, but eta 1 is not eta 2. So now, if I want first, if I want the incident power density, this is going to be the incident wave. It's 1/2 times the magnitude of E naught incident squared over eta in region 1, which is just eta naught AZ. Right? You can tell me what that is if you don't mind. Incident electric field is 2.825. Got to square that and divide it by 2 eta naught, or by 245. meter squared AZ. Y'all agree with that? Is that right? Anybody else do that or not? If you take 2.825 and square it and divide by 245.
And then also divided by 2 again, so.
I got, 0.0105.
0.0105? Watts per meter squared?
Yeah.
Okay, anybody else? You got that? All right, what's the reflected field? Staying with 1/2, right? Now you need the reflected field strength, which is, call it 1.7. I'll just put it here, 1.7, square it, and divide it by 8 0, right? It will be in the minus AZ direction. So it's minus what?
0.003.
Say again?
I got 0.003.
Okay. 0.003.
38.
38 AZ, and that's watts per meter squared. Finally, what's the transmitted? If you add those two together, it'd be the transmitted, but transmitted electric field is what? 1/2 magnitude of the transmitted field. I don't even know where that is. Did I erase that? It's somewhere. Anyway, the transmitted electric field squared over 82, and 82 is 8 0 over 4, and this would be in the AZ direction. Now, if you add these two together, you will get the transmitted power. Or you can go to this calculation. Frankly, I don't remember what the transmitted field is. Anybody? Did anybody write it down? Say again? 1.13, it sounds right. Alright, so we take 1.13 and square it, and then divide it by 8 0 over 2, or divide by 8 0 over 2 would be AZ. We should get the right value. Can anybody give that to me?
0067.0067.
Watts per meter squared. Now, if anybody has the time to add this and this, or subtract this from that, you should get that. Y'all follow me? That works. So now we've got the reflected power, incident power density, transmitted power density. We've got all the electric field everywhere. We didn't get the H field in the first region for the incident reflected, but you all follow the tactic. Now I gotta tell you, this is one thing you have to be careful of. When I say that the reflection coefficient is equal to E naught incident, or E naught reflected, pardon me, over E naught incident, right there, the transmission is equal to the transmitted electric field over the incident field. Those are electric field quantities. They are not equal to the H field transmitted over the H field incident. Y'all follow me on that? These are defined in terms of the electric field, and they won't be the same. So if you come here and somebody would say, this is true, it isn't. It'll be different. And that's something you gotta be aware of. I see this on final exams. People will do that. They'll say, well, he's asking, if I've got the E field ratios, I've got the H field. That's not true, because the H field, remember, is the E field divided by eta, and the etas are different in these regions. So please make sure of that, all right? Always get the electric fields using those the transmission and reflection coefficients. Okay, that's the last topic. From here on, it's just gonna be going through problems on this and review. Okay. All right.